Hello, today I'm going to be recording how to do a Bayesian linear mixed model. The data set that I'm using today is from Bliese and Halverson 1996, and it's publicly available in the multi-level package in R. This data set examines individual level data from soldiers across 99 Army companies, and each Army company has on average 75 soldiers. In total, there are over 7,000 soldiers in this study. So the research question that I'm interested in is how group work hours and individual level work hours predict soldier well-being. So this is inherently a multi-level question because I'm interested in the effect of work hours at the individual level as well as at the group level in predicting soldier well-being. So to get started, I'll go ahead and select mixed model and then Bayesian linear mixed model. And we'll go ahead and drag and drop well-being to the dependent variables box. And then we'll drag and drop W dot hours to the fixed effects box and G dot hours to the fixed effects box. So what does this mean? Going back over here, G dot hours is the average level or the average work hours within each group. So here we have the individual level work hours. So this person worked 12 hours, this person worked 11 hours, so on and so forth. So the average of this whole group is about 11 hours. We can look at our group mean centered hours to understand how much each individual differs or deviates from the group mean. So for example, this first person worked about 12 hours and the group mean is about 11 hours. And so the group mean centered hours is about 1, right? Because they are about 1 hour above the group mean. Right here, we can see that this person is about 2 hours below the group mean. So to do our analysis, let's go back over here. Let's drag and drop our grouping variable to the random effects grouping variables box. And then under model, let's go ahead and unselect everything except for intercept because we first only want to look at our varying intercept model. And we'll also get rid of this interaction term. And this might take a second to load because it is going through a sampling process. So I'll come back once it's produced some results. Okay, so here we can see our estimates for the intercept and for the individual level hours and group level hours. So to interpret this, we might say something like, for every 1 hour increase in work hours at the group level, predicted well-being decreases by about 0.17 points. And for every additional hour worked at the individual level, well-being decreases by about 0.05 points. If we look at our 95%, these are credible intervals. They do not overlap with 0, so we have sufficient evidence to conclude that our estimates are actually predictive of well-being. R hat is a measure of convergence, and values less than about 1.1 are considered sufficient, or in other words, it suggests that the chains have adequately converged on a value for this estimate. ESS is also, it's called effective sample size. And it's essentially the number of observations, in this case, in the bulk, so in the center of the distribution and in the tails. And the goal here is to just ensure that there was adequate sampling of different regions of the posterior distribution. ESS is also related to autocorrelations. Based on this table, our R hat is less than 1.1 and our ESS is greater than 1,000 in both cases. So we have some evidence to suggest that the chain converged and adequately sampled the posterior distribution. So now I'll go ahead and let's look at our model summary, fixed effects estimates, variance correlation estimates, and random effects estimates. Another thing to note, JASP automatically samples about 4,000 samples or steps on each chain. And it did 3 chains by default with a burn-in of about 2,000. That means that about 2,000 samples were discarded at the beginning, before it actually starts sampling, and this is what's included in our analysis. Adapt delta is the average target acceptance for whether or not like the proposed value within like the algorithm is accepted. And then the maximum tree depth is just the number of evaluations per sample. And I typically leave these to the default settings unless there's issues with convergence, or there are like divergent transitions, for example, and then that's when I want to come back and increase adapt delta or tree depth. Okay, so our fixed effect estimates, they're the same as above. And then we also have our hat and effective sample size. Finally, we can see with our varying intercept that the intercepts for the within group work hours have an estimated standard deviation of about 0.12. So now a good practice is to make sure you set your seed, especially when we're doing Bayesian modeling, where different seeds might lead to slightly different variations of estimates because we are sampling. But typically the changes are very minor. Now to do a varying intercept and slope model, we'll go ahead and select mixed models and then linear mixed models under the Bayesian tab. Now we're going to select the same variables as before. We're still predicting well-being from group mean centered work hours and group level work hours. And then we'll also go ahead and we're going to get rid of the interaction term, but we want to make sure that everything is checked to look at the varying slopes. And then we'll wait for this to load. Okay, so we can see our estimates as before, our 95% credible intervals. Again, they don't overlap with 0. Our hats are lower than 1.1. And our ESS, effective sample size, bulk and tail, looks like that the algorithm has sufficiently sampled the posterior distribution. So let's go ahead as before and look at the model summary as well as the fixed effects estimates, variance and correlation estimates, and random effects. Okay, so we can see our model summary as well as the fixed effect estimates. As before, for every 1 hour increase at the group level, well-being decreases by 0.17 points. And for every 1 hour increase at the individual level, well-being decreases by 0.05 points. Now, if you watch the frequentist linear mixed model example, you might have noticed these estimates are identical to one another. So both paradigms are giving us similar results. Okay, now we can see our standard deviation for the intercept is 0.11, and then the standard deviation for individual level work hours is about 0.03, so that's really small. And we can see the correlation here. Now, if we wanted to compare models, we can go ahead and look at, we might want to look at the leave one out cross-validation LU in this case, because it looks like the wake estimates are unreliable. So our LU value is about 19176. And in the previous model, it was about 19175. And the standard error is so large that it appears that both of these models perform well in out of sample prediction. And so in this case, we'd probably favor the simpler model, since the model with varying intercepts and slopes does not perform substantially better. You might have noticed that in these analyses, I did not specify the prior, and that's because JASP does not have functionality yet to allow users to specify the prior distribution for multi-level models. The prior that is used is a default, and it's actually an auto-scaled prior from the RStan-ARM R package for linear mixed models. So it applies an exponential distribution to the standard deviation of the random effect, and then an independent normal distribution centered at 0, and then auto-scaled based on the data to be weakly informative for the fixed effects. If you're interested in learning more about the analyses I just conducted, you can check out our paper in the PAIR journal. I have detailed how to do this analysis in JASP, and there are detailed instructions as well as notes for interpretation and screenshots for step-by-step guidance. Okay, thank you so much for watching.